Alright, now today we are talking about lesson 10-3, which is the area of regular polygons. Hopefully you remember what a regular polygon is. If not, just a quick refresher. It has all of its interior angles are congruent, and all of its side lengths are congruent as well. So it has congruent interior angles and congruent side lengths. Okay, so we're going to start off in part one here. We're going to look at a somewhat of a proof as to how to find the area of a regular polygon. We're also going to look at some parts. There's a little bit of new vocabulary here, and we'll look at one example. And then part two, we'll be looking at a couple more examples, because they can ask a lot of weird questions about perimeter, about area, about the length of certain sides, etc. They can ask a lot of weird questions. So we're going to look at some questions that you could see moving forward. So let's get started. So we are given here a regular hexagon. We're assuming they either told you that it's regular or it's labeled as such, but we're going to assume that they told you it's regular, just so my picture stays, nice and clean. So let's say we know it's a regular, it has, 6 side lengths, so it's a regular hexagon. Now there's a couple key things, pardon me, a couple key things, or key parts that we want to call, or that we want to name. The first is this segment length here. This segment length is called the radius. And you may have heard this term before. Radius is the term for a circle, right? From the center to the edge of a circle. So why is that used here? And again, this is going to be a rough sketch here, so bear with me. But if you can imagine this hexagon inscribed in the circle, meaning it looks something like this. Okay, so imagine there's a circle that inscribes this hexagon around. Well then, what is this side length in pink here that I'm highlighting again? What does it have to do with the circle? Well, again, it's from the center of the circle to the edge, which is why it's called the radius, right? So that's where that term comes from. That's the radius of my regular hexagon. There's another line that I have marked here. I'm going to highlight it in green. This line is called the apothem. You may not have heard this word before. It's a weird word. Sounds like a possum, like the animal, but it is not that. So this is how it's spelled, apothem. Some people say apothem. I say apothem. You say tomato. I say tomato. Right? Same difference. So apothem. And what that's referring to is from the center, which I didn't label the center yet, so this point here is called the center, meaning it's equidistant from each side length. But from the center, the apothem is the distance to the side length. So the center measures this distance here, or the center to the side length is this distance here. That's called the apothem. We know it's the distance because it's perpendicular to the side length. So remember that the apothem is perpendicular. Okay, so that's kind of the key thing for apothem there. Remember that it's perpendicular to the side. Let's see, what else do we have here? We have just a normal side length, right? This is just called the side of it. No special name there. The only other thing that you're really going to see is this thing called a central angle. Okay, it's called a central angle. So if I'm going from the center here and I create a triangle, well then this central angle, or in the center, we've formed an angle. We've formed an angle, which I'm highlighting in blue here. Okay, this angle is called the central angle. Right? Not too clever of a title. It's called that because it's in the center and it's an angle. Right? So this is called the central angle. And it's really not that hard to measure the central angle, because you can imagine that if I have 6 6 of these triangles drawn in as such, right? Well, then what does this form in the middle? Well, this forms a circle right here, right? It forms a circle. It goes all the way around, which means in that we have 360 degrees, right? But it's 360 divided into 1, 2, 3, 4, 5, 6 congruent triangles, right? 6 congruent angles. So the central angle is just figured out by dividing 360 by your number of sides, right? The number of sides, which in this case is 6, which means each central angle for a hexagon, each central angle is 360 over 6, which is 60 degrees. Now, the only other thing you'll need to know here is that the apothem, when it drops down, it forms an angle bisector, meaning it cuts this central angle into 2 congruent pieces. So with a hexagon, it's convenient. If I don't want you to use a calculator on a test or something like that, I can give you this problem because it forms, well, the central angle is 60 degrees. You cut it in half, that means each of these must be 30 degrees, right? So it forms a 30, 60, 90 triangle. There's 2 of them, or 12 of them if you're talking about the whole hexagon. So anyway, we're going to use those terms throughout the chapter. So if flashcards help, use flashcards. Some of them are pretty self-explanatory, like central angle and center. Radius, hopefully you can remember just the inscribed circle. The only new term you have is apothem. That should be the only brand new thing you have. Okay, well, let's look at a proof of how to find the area of such a shape. Now, if I'm dealing with, again, I'm going to show you a regular hexagon. This works for all regular polygons. Okay, so the area of regular polygons. Again, this works for all of them. I'm just going to show you the hexagon because I think it's, it's visually appealing. It's nice. It's a nice shape because of the 30, 60, 90 triangles and such. But let's look at how we do this. So the strategy, we've used the strategy before. If you look at the previous videos, we've used the strategy where we have, where we're going to cut, actually that was a terrible triangle. We're going to slice this triangle into, did I say triangle? This hexagon, I'm sorry, into triangles, because then we can find the area of, for example, one of these triangles, and then we can find the area of another triangle, and then another triangle. We can keep finding the area of each triangle and add them up, which will then give us the area of the hexagon. But, since it's a regular polygon, each of my central angles is congruent, right? Each radius is congruent. Each side length is congruent, which means each of these triangles is also congruent, right? Each of the triangles is congruent. So if I can find the area of, let's say, one of these, well, then I can just do what to it? I can multiply it by 6, right? The area of the hexagon is just 6 times the area of that one triangle. So let's look at how to find the area of that triangle. If I have, let's call this side length here S, for side length, okay? If I want to find the area of this triangle here, what do I have to do? Well, it's a triangle, so the area is 1/2 base times height, right? The area of the triangle is 1/2 base times height. Currently, we do not have the height, because again, the height meets at 90 degrees. So if I draw the height here, right? If I draw the height there, it goes from the center to the side length, and it meets at 90 degrees, okay? So the base of this triangle, I'm going to highlight in pink here, the base of this triangle is just S, right? So I'm going to write this as 1/2 S. Well, what's the height? Do you guys remember the vocabulary word that we just learned? Right? We could call it H, but what type of line is this? From the center to the side length, meeting at 90 degrees. Well, this is just our apothem, right? This is the apothem, so let's call it A. Right? So this is 1/2 S times A. S times A is the area of that triangle. Now, we have 6 of these. So we would end up, if we want the area of the entire hexagon, okay, the area of the whole hexagon, it would just be what? 6 times 1/2 SA, which you could multiply together and get 3 SA. But that doesn't show us the thing in general, because here's kind of the cool thing about this. If we have 6 times, actually I'm going to change color so you can see it better. If we have 6 times the side length, because I can write these in any order I want, right? I could write this as, equals, this is 6 times 1/2 times S times A. I could write it as S times 6 times A times 1/2 if I wanted to. I don't know how I would want to do that, but I'm able to do that because of the commutative property, right? Well, I think it's convenient to write it like this. 6 times, I'll write the number in front, 1/2 times 6S times A. Now, why would I choose 6S? Well, if you think about it, 6S just means that you're starting with one of these side lengths. You have another one that's 2, another one that's 3, another one that's 4, another one that's 5, and another one that's 6, which means we just formed the what of this hexagon, or this regular polygon. Well, 6 times S is just your perimeter. So really, this is 1/2 the perimeter of this polygon times the apothem, which sometimes you'll see it as 1/2 PA, sometimes you'll see it as 1/2 AP. I usually write it as 1/2 AP. So the area of my regular polygon, and that's true for squares, it's true for equilateral triangles, it's true for regular pentagons, regular hexagons, regular decagons, regular whatever. That's always going to be true. Okay? Let's look at an example. So here I have a regular, assuming they tell you it's regular again, I have a regular pentagon. So for all of you who say, well, they don't tell you it's regular, now it's marked. So it's a regular pentagon, and all they give you is this brown segment, which has a length of 10. Well, what's that brown segment called? It's called I hope you remember, it's called the radius. From the center to a vertex is called the radius. So the radius is 10. Well, the objective here is to figure out the area of that, meaning we need what? Again, area is just 1/2 AP. Well, do we know the apothem? No. Do we know the perimeter? No. Do we know the area? No. So what do? Well, there's a couple options. One is to cry. I don't recommend doing that one. We should actually try to figure this out. Again, the strategy is always pretty much the same, and it is this. The strategy is pretty much always going to be create a triangle. Okay? Create a triangle. Now, when you create that triangle, that was terribly drawn. I'm drawing some awful triangles here. When you create this triangle from the center to the vertex, you then create what? Well, you form this central angle. Well, do we know what this central angle is? We should. There's 5 of them. If we drew all of them around here, there's 5 of them. They're all congruent, which means, again, it forms 360 degrees, right? And you divide that into 5, which means each central angle must be what? So the sen-ang, the measure of the central angle, is 360 divided by 5, which is 72 degrees. Alright, so if I know that's 72 degrees, if I draw my apothem straight down here, then it cuts it in half, meaning each of these angles is 36 degrees. Alright, so you have 36 degrees. Now what do I need? I need 2 different sides here. I need 2 different sides here. I need A and a P. I'm going to use my trig functions to find both. Okay, I'm going to use my trig functions to find both. So first let's find we'll find A. And how do we do that? We have, well, you know what? I'm about to run out of time because I can only do a 15-minute video. So, suspense here. I'm going to leave a cliffhanger here. I'm going to continue this problem on part 2, where you can watch how to figure out the rest of this. Okay? You can figure out how to watch the rest of this. Just real quick, using trig functions, you should be able to find A. You should be able to find X using those right triangles if you don't want to watch part 2. But I'll show you that in a minute.